Okay, let me begin by thanking the organizers at CHEP for providing me with this opportunity. So, I'm going to talk about the measurements at KamLAND and JUNO, which are reactor neutrino experiments. And the new physics scenario in focus is scalar NSIs, okay? So the first few slides are really basics about neutrino physics. It's targeted at audience members for whom this might be new. So now we all know that neutrinos oscillate, and the main evidence for this was basically two kind of anomalies. We had an anomaly in the solar neutrino measurements, where the number of electron type neutrinos which were being seen were not in conjunction with the standard solar model, okay? At the same time, there was also this atmospheric neutrino anomaly where neutrinos which are coming from above the detector and the neutrinos which are coming from the diagonally opposite side of the detector and were traveling the entire length of the Earth were also not, and they were not matching each other, and the cosmic ray flux is isotropic, so one also expected the neutrinos to be isotropic and equal in number. So the easiest way to describe both of this was to just say that neutrinos are massive. In the standard model, neutrinos were assumed massless. So the most economical way, the least you had to do was just tell that neutrinos are massive, and at the same time posit that weak eigenstates must necessarily not match with the massive eigenstates or the energy eigenstates, okay? So from the LEP measurements, we now know that neutrinos come in three kind of flavors: nu e, nu mu, nu tau. So their flavors are defined as per the charged lepton or the charged lepton partner that accompanies them in their weak interactions. And yeah, so here we have three kinds of weak eigenstates, and these are the actual physical particles, the mass or the energy eigenstates. The energy eigenstates in vacuum would simply be the mass eigenstates. And the thing about neutrinos is that they can be produced and detected only indirectly via weak interactions. So all we see is the charged lepton, and we deciphered that there was a neutrino by seeing the charged lepton. However, they propagate as mass eigenstates, and just by doing a very simple quantum mechanical time evolution, a Schrodinger-like time evolution analysis, one can derive the probability that a neutrino which maybe was initially produced with a given flavor can later be detected as some other flavor, okay? So in the previous slide, I have this small plot here. So the charge partner or the flavor here is electron. So this nu is of the electron type. And if this neutrino is produced and detected very quickly, just after production in some manner, then you would always observe electron as the charged lepton in the detector as well. However, if you let the neutrinos travel over a certain distance, then that neutrino a neutrino which was produced along with, let's say, muons, might give electrons in the detector, okay? So this is basically what is neutrino oscillations or flavor oscillations, and there's a complicated expression here. It's not really complicated. So basically we have this mixing, which is not identity, because the weak eigenstates and the mass eigenstates do not correspond to each other. Okay, so this is the situation in the full three neutrino, the standard framework, where we have three active neutrinos, and these depend on the three mixing angles between the mass and the flavor eigenstates, and they are parameterized by three mixing angles. And in addition, we also have mass square differences. So oscillations do not depend on the absolute masses of the neutrinos, but they only depend on the mass square differences between the three eigenstates, and there are only two independent mass square differences that we can make from three eigenstates, okay? So as I showed before, all those mixing angles and the mass square differences sit in this probability expression. So by measuring these probabilities, one can get an estimate of what these values are, and that is what we have from all these experiments. So this angle θ23 is particularly measured by the super beam and the accelerator and the atmospheric experiments. θ13 comes from the short baseline reactor experiments, and θ12 comes from solar neutrino experiments as well as the long baseline reactor experiments. So there is a sector in these oscillation parameters which are now known very precisely to almost 1% precision. So we know the values of sine squared θ12, delta m square 2 1, sine square 2 theta 1 3, etc. very precisely now. At the same time, we have some other parameters or other unknowns in the theory, which are not that, we do have some initial indications or hints, but we really do not know very well about them. And in addition to that, the neutrino experiments are also rife with different kind of anomalies. Okay, so as an example, for the last several years at least, there is the T2K and the NOVA experiment, which are accelerator experiments. And while one of the experiments is telling that CP is close to conserved, the other is telling that CP is maximally violated. Okay. Okay, so this is the 3-flavor framework. The experiments that I'm talking about today are actually simpler, and they can be described only by 2 flavors. So one really doesn't need to work with 3 mass eigenstates. Effectively, the oscillations are essentially happening between a given flavor and some other linear combination of the other 2 flavors. Okay. So in that case, the expressions are actually much simpler. So, there is something called the disappearance channel, where you have an initial flux of, let's say, the electron type neutrinos, and in the detector you are trying to see again the electron type neutrinos only. So you measure actually what is the depletion in the flux. So let's say you started with some number of electron neutrinos. In the detector you will find that some of it's depleted, the number is less than what you started with. Okay, so that depletion is given by this probability, which is called as the disappearance channel. And the one minus of this is basically the opposite, the other scenario, where you started with a nu e, and in the end you are not getting a nu e, but let's say a nu mu or a nu tau. Okay, so here you can see that there is the mixing between the weak and the weak and the massive eigenstates, which is this mixing angle theta, and along with that there is the mass square difference dependence and the distance that neutrino is traveling and the energy of the neutrinos. So the ratio L over E directly tells me which delta m square the experiment is going to be sensitive to. For example, we can have these 3 kind of scenarios, or actually we have different energies and different lengths available, so they have sensitivities to a wide range of mass square differences. The relevant ones for reactor experiments are the reactor very long waistline, which is sensitive to the solar mass square difference, which is 10 raised to minus 5 eV square. And then there is the diabe or the reactor not so long or less longer, medium long experiment, which is sensitive to 10 raised to minus 3 eV square. In addition, if there are additional sterile neutrinos, which is a different topic, so if they are of the order of 1 eV or 1/10 of an eV square, then you would expect oscillations happening at much shorter baselines, such as only 10 meters away from the source of the neutrinos. Okay. So in this talk, I'm only going to talk about the reactor antineutrino. So let's look at the fluxes and the cross sections that we deal with. So these are the nu e bar, the electron antineutrino fluxes, which are coming from the reactor, and it's basically an exponentially falling kind of behavior, and the expression is given here. So as a function of energy, we have nu e flux, which is falling. This is the inverse beta decay cross section. So in the end result, you have a neutron and a positron and a neutron and a nu e. So basically, by tagging the nu e or seeing the nu e, we can understand what is the antineutrino energy. So that cross section goes like this. So there is an exponentially falling flux and there is a rising cross section. So you expect the events, unoscillated events, or the signal to be a product of these 2 lines, which is this green line, okay, which is what is seen here. So this plot is for the experiment JUNO, which is an upcoming experiment. So it does not have data. It's supposed to start taking data sometime this year or maybe next year. So the black curve here tells you the unoscillated event rates, and if oscillations are happening, then that is going to get depleted to this red or the blue curve, depending on the mass ordering. So one of these colors is for the neutrino mass ordering, for the normal ordering, and the other one is for the inverted ordering. So the depletion from this black curve would directly tell you what is sine square 2 theta 1 2. The dip of the minima of this oscillatory pattern tells you what is the delta m square 2 1, and by measuring which is before, which line is leading, which line is lagging, you can get an estimate of the neutrino mass ordering also. So these are the main aims of this experiment JUNO. It is expected to give us a very precise measurement of sine square 2 theta 1 2, the mass square difference delta m square 2 1, and it is also with some terms and conditions, it's also predicted to or expected to give a very good measurement of the neutrino mass ordering, close to 3 sigma or maybe slightly higher. Okay, so the other experiment that I've considered in this work is the KamLAND experiment, and this experiment has already finished data taking. It ran from 2002 to 2012. It is also a reactor antineutrino experiment, and it basically constrained these two parameters, tan square theta 1 2 and delta m square 2 1, which is relevant for the electron neutrino disappearance for the KamLAND baselines. And as you can see, so the blue contours here are the results from the solar experiment, and this colored contours are the ones from KamLAND. So the estimate on theta 1 2 is essentially coming from the solar experiments, and the measurement of delta m square 2 1 is coming from KamLAND. KamLAND doesn't constrain theta 1 2 very well. That's better constrained from solar, and solar doesn't constrain, solar results do not constrain delta m square 2 1 very well. Okay, but together they can constrain delta m square 2 1 and tan square theta 1 2 very well. And this is our current precision on these two parameters. On the right hand side, I have this JUNO experiment, and this is its mass ordering or mass hierarchy discovery sensitivity. So for these choices of the two parameters, it can distinguish between the normal ordering and the inverted ordering close to chi-square 16, which is 3 sigma or so. Yeah. And it can also measure theta 1 2 and delta square 1 2 1 to very great precision, sub-percent, less than a percent precision. Okay, so in this work, what we have done is we have taken a model for non-standard interactions, and we have first found out the constraints on non-standard interactions using the KamLAND data, and then see what kind of measurements will happen at JUNO if NSIs turn out to be the true case. Okay, so this is our effective Lagrangian. But so basically, there is a scalar field phi with the mass m phi, which can couple two neutrinos via non-standard interactions, and this is a scalar field. So it's called scalar NSI, and this is the effective Lagrangian. These are Yukawa couplings of the field with the fermions and the neutrinos. This is the mass of the field. This, I believe, is a paper by Neves and Palashpal. So that's where this idea is from, one of the first papers. So with this Lagrangian, the effective Hamiltonian becomes like this. The difference from the vector NSI is that in the case of vector NSIs, the NSI come up in the matter potential. In contrast to that, the NSIs in scalar NSI are actually coming in the mass matrix. Okay, so this delta m is the NSI term, and it's getting added to the vacuum mass matrix, and that is how this Hamiltonian will get affected in the presence of NSIs. Okay. So this is the vacuum m, the vacuum mass matrix, and so we parameterize all these 3-4 parameters effectively as some other parameter, and we just call them as etas, and we scale them by this delta m square 3 1 square rooted. So this basically is our NSI matrix, which is getting added here. Okay, so these are some analytical expressions that we calculated. I'll not go into the details. So there are some parameters which are basically the NSI dependent parameters. We expect these NSI values to be small, otherwise we would have already seen them or deciphered them indirectly via anomalous measurements. Okay, so these values are expected to be small. So all these three epsilons are dependent on the NSIs and also the other mass, other oscillation parameters. Note that the NSIs here in this case do not depend on mass square differences, but only on the absolute masses of the neutrinos. Okay. So what we find is that in the scalar NSI situation, theta 1 3 and delta m square 3 1, the vacuum or the measurements at Diabay which measure near vacuum delta m square 3 1 and theta 1 3, those are not getting affected by the eta EE. So in this work we only considered one of these parameters for simplicity, because even adding 2 leads to very complicated expressions and also huge runtime. So as an example, we have only considered this EE, which is the channel involved, nu E bar to nu E bar or nu E to nu E, and it's only this parameter we have made non-zero. Okay, so so we find that theta 13 and delta m square 31 are not going to get affected by scalar NSIs. So the measurements from Diabay are expected to be robust measurements. So whatever is the current understanding on theta 13 and delta m square 31 will continue to be even if NSIs are present in nature. We can't say the same about these two measurements, tan 2 theta 12 basically and delta m square 21. These do get affected and the changes are not very small. So what happens in this case is that the corrections here are suppressed by theta 13 or square of theta 13, and since theta 13 is a small number, the corrections are also small. These are the effective expressions for the probabilities for KamLAND and JUNO. This is a simple two-flavor expression. This is very small, so it's almost zero. So essentially, and we can approximate this equal to 1. So it's essentially this 1 minus this thing kind of expression that is at work. In the case of JUNO, we have an interference term between the two mass square differences, 3.1 and 2.1, and it's basically here that the hierarchy or the mass ordering sensitivity is present. Okay. So before we go on to the results, there is a discussion that I want to do regarding the measurements. So basically, if NSIs are present, that anything that you have measured or any neutrino oscillations, that parameter that has been measured is in the presence of NSI. Okay, so it's some kind of an effective expression, and there is no way to do this. At least we don't have a data which corresponds to some vacuum oscillations. So whatever measurement we have, if NSIs are true, are with NSIs. Okay, so. So one of the ways in which the constraints or NSI or discovering NSI, scalar NSIs are proposed is to consider the reactor neutrino measurements as the benchmark. So you call this to be your vacuum values because the baselines are too small, so the densities are expected to be very little. So hence the NSI effects are also expected to be very little. And you calibrate your longer baselines or larger densities in terms of what you measure at the short baseline reactor experiments. Okay. In this work, we have followed a different approach where we have just simply assumed that NSIs are true. So that makes it a very model-dependent analysis. But once we do this, we in principle can fit KamLAND data. So we have a theory which has NSI into it, and we are just fitting KamLAND data and asking what constraints are obtained. So these are some probabilities for JUNO with this 53 kilometers and KamLAND with 180 kilometers. So there is a black curve which corresponds to when there is no NSI present, and then there are the colored curves, the red and the blue curves, which correspond to different values of NSI. And as we can see that there are significant differences even if you take very small values of NSI. So this is, for example, 2 times 10 raised to minus 3, etc. So even such small values can affect the amount of depletion, and it is also shifting the location of the minima. So it's affecting both the mixing angle as well as the mass square difference. Okay. These are the same plots with events at the level of events. So we observe the same behavior at the level of events also. And on the left panel, I have just shown the IBD events as a function of energy. In the right panel, we have the relative change compared to the standard situation. And this is KamLAND, so this is actual data, while this is a simulation here. Okay, so we first do a KamLAND fit, and what we find is that so KamLAND is able to constrain NSI in some range, but at the same time it allows very large values of theta 12 and delta m square 21. So the true value sits somewhere here, 33 degrees, but what we find is that values as large as 80 degrees also, and as small as 10 degrees also, with some different values of delta m square 21 are allowed by the data. So here we have taken four set of representative values which are allowed by the data, and now we have now we run JUNO and find out what kind of constraints can be derived for these sets of delta m square 21, theta12 and the NSI parameter eta EE. So KamLAND can constrain eta EE, the NSI, between values ranging from -1 to 1. So while doing this fit, we have marginalized in that range, and what we find is that whatever turns out to be the measure, this is 100,000 events. So what we find is that even if you have NSI, so JUNO is going to give you constraints which are not ambiguous. So the allowed region will be centered. The best point, I mean, the input value is centered around the allowed region. And while you may measure very different values, such as this is 55 but the allowed region is going to be centered around this. Okay, so that is a robust measurement by JUNO. However, JUNO is not able to constrain NSIs any better than KamLAND. So we will not be able to. So in this model dependent way, we will not be able to constrain NSI, but one thing we can conclude is that JUNO can give very robust measurements of theta12 and delta m²21. So that is one main result. The other thing is that theta12 is actually not constrained the best by KamLAND. So eventually we must have constraints from solar experiments also, and that is work in progress. And these are my conclusions. So the main thing is that so many works are happening with scalar NSIs, and it is very tacitly assumed that the existing measurements of the oscillation measurements that we've already taken are robust, and let's just proceed with them and find out the constraints on NSI. Just by taking the KamLAND data, we have seen that theta12 and delta m²21, which are very different from the current best fits, are actually getting allowed. We also show that JUNO is able to do a better work, and it is unambiguously able to measure these parameters. So the stress is that one needs to first fit the existing neutrino data with whatever new scenario one is considering, and then go for the more challenging questions such as mass ordering or CPU violation. Okay, so that is all. Thank you.
Yes, so your scalar NSI does not have an energy dependence, right?
Yes, it's not energy.
So the assumption itself that in reactor neutrino experiments, the effects of scalar NSI would be too small should not hold, because the reason that Dune has more, let's say, matter effects is not just because Dune has long baseline, but also because Dune has higher energies.
Yes.
So that assumption itself doesn't hold, right?
No, so vector NSIs are dependent on energies.
But scalars are
Scalar NSIs are not dependent on energies, but they are dependent on
just the density.
They are dependent on the fermion that is present. Okay?
Yes.
So you have more density in the case of let's say Dune, and lesser in case of reactors. There is nothing lesser than reactors. Okay.
Correct.
So there is no vacuum measurement. So whatever is the reactor becomes the least NSI affected measurement that I have. Okay. So whatever I'm measuring, if NSI is true, that's an effective measurement. Yeah.
Yes, but for reactor neutrino experiments, this average density would be somewhere around 2 grams per something.
Yes,
like,
but
I mean,
I have to compare it with something which is vacuum, and I don't have the vacuum result.
Yeah. So
vacuum
you fit, you do a joint fit.
Yeah.
Understood. Thank you.
Any more quick questions?
Okay, I just have a quick question. So how do you treat the systematics when you do the fit? Because it's you're looking for some effects which is like
yes.
on top
So
of the
I didn't discuss the details of the computation itself, but we have. So okay, as far as KamLAND is concerned, we have been able to reproduce the exact results as that of the experimental collaboration. Our analysis is certainly simpler than what they consider. So we have not considered systematic uncertainties at the level that experiment does, but we have the benchmark values, 5%, 10%.
Yeah, I think since you're looking for looking at the energy spectrum and you're looking for effects on top of standard oscillations.
Yes.
This energy, if there are energy dependent systematics, then I think you should be carefully looking into it. Because
So
that
we
would
have
actually-
taken, in the paper describes the details of the systematic
even
uncertainties.
the correlation between the beams.
Yeah, so we have taken those things into account. Yeah, both for this as well as JUNO, we have not taken the non-linearity. That's a technical detail of the JUNO experiment. So that is not something we have considered.
So other questions may be taken offline. Let us thank the speaker again.